count as the same. And the next one is called kinetic theory model. I am going to talk to you about the actual expression about what that means. So essentially, total pressure is, you summarize all the pressures xi. So what I'm saying is, you have a gas A, gas B, just sum it together, all the gases, and this one, each partial pressure is just nothing but NART divided by total volume. And E, B, NB, RT divided by total volume. So regardless of the chemical species that you're dealing with, all you need is counting the number of gas molecules, and then you will get the same answer. So the total volume, it's just repeating the same. N is Na plus Nb, XA is Na divided by total N, and this equation should make sense to you. Want to get back to you on this. So it's the whole idea is the pressure. This equation is probably easier for you to see. Regardless of chemical species, they are in the same temperature, same energy. So each collision will contribute to the total pressure. I'm not discriminating heavier gas or lighter gas, because lighter gas moves very fast. And heavier gas move very slow. And I'm going to show you do you know how fast the gas molecule is moving in this room? Can you make a guess? Has anyone even thought about how fast the gas is moving in this room temperature? No. This is just an extra. 100 miles an hour. This is, if you can throw the 100 miles an hour ball as a baseball player, I think that probably you will not sit here if you go to the Major League Baseball. This is pretty fast, right? Gas molecule at room temperature is above moving 1,000 miles an hour. Okay? Very fast. So we just do not feel the pain because it is so light, so we don't feel it. And when you move fast enough, speed. Okay. So the problem that I like to recap with the partial pressure is this is all the PDF file has been scanned. My lecture note is there, so you guys can look at that. I like this room. I like this question that in the practice problem. So let's look at the problem. I'm talking about the room of a reasonable size, and then the volume itself is 400 square meters. That's a pretty big. I would say the size of this room, right? So they are asking us if this is the size of this room, and if you bring your relative humidity in here is 60%. And the temperature here is at 27 degrees C. So then how many mass of H2O in this box, in this room? Okay. So I think this is about the size of this classroom, how many grams or kilograms of water we are talking about, and this is what we have to calculate. Okay? So in this room, what they're saying is, because they give a relative humidity information, we have an oxygen, we have a nitrogen, but more importantly, we have a water. Right? And the relative humidity is something that they, in your exercise problem, throw it at you. Relative humidity is defined by pressure of H2O, partial pressure, okay, when they are saturated. Okay, so this is a saturation equilibrium vapor pressure. and the actual vapor pressure of water as a partial pressure in this relative humidity condition. So it's a 60% is 0.60, and that's the first clue that I have. Okay. And then you have to look for this. What is the vapor pressure of saturated water? And you have to look at the textbook and 35.6 millibar from the property table. So there is at 27 degrees C. So this saturated vapor pressure means when you have system and when they are in equilibrium, and there is nothing but just the water vapor, and there's a water as a liquid, and the vapor, the pressure as it is a saturation on the equilibrium condition of the H2O, and then this is going to be taught in the actually chapter 4, okay? Clausius-Clapeyron equation and temperature dependence on the vapor pressure. We're going to talk about it. But I just wanted to use this information that I know the saturation vapor pressure, and the definition of relative humidity. So I got the most crucial information, partial pressure of water, which is I do care, is just nothing but 0.6 times 35.6 to the 10 to the minus 3 milli, 10 to the minus 10 to the 5 Pascal. Okay, that's a bar, that's a millibar that I was. So I already kind of choose myself to use the Pascal as my pressure unit. So I got this, and then P V equals nRT, so that's H2O, H2. So I need to figure out, giving you the partial pressure, giving you the volume, giving you the temperature, you guys can calculate your N, right? Once you know your N, what is an H2O N? Number of moles. So that's the mass divided by molar mass, right? All right. So that's what you need to do, and this is what they want. So I'm going to use a symbol, small n, big N as a molar mass, and I'm going to plug that in. PV M over small n RT. And I want to rearrange this equation that mass is M times RT. M is M times PV divided by T. So I think that I got my whole information. This is a pressure of H2O. So that's the mass of H2O. And then this is the mass of H2O molar mass. So this is a sort of the kind of the variation of ideal gas law, and then I just have to plug the numbers. Okay. And there is some difficult part here. So far is easy. Okay. The trick, I would say not a difficult. The tricky part is my information is based on the Pascal here, right? So I'm going to use volume in a unit of square meter, and obviously I'm going to use this as a Kelvin. And what's my choice of an R? That's right, 8.314. And you don't have to remember the number, by the way. Yeah, that's right. It's a joule divided by mole Kelvin. So if you do that, and then what do you put it in here? Molar mass.
18.
That's right. Now This is not, I guess I'm making a small thing in a big deal, okay? But molar mass of 18, what is the unit?
Grams per mole.
Gram per mole. And do you remember Pascal, Joule? This is all MKS unit.
Kilograms.
Yeah, so you don't feel comfortable here, right? So then, I'm not gonna do that. So 18, 10 to the minus 3 kilograms per mole. Like this is like what, 0.0018 kilograms per mole, right? You guys can plug the numbers here, and plug these numbers, Pascal, 400 cubic meters, I don't know, something like 300 kelvins and 8.1.4. And then what unit do you have? You will have a kilogram.
Wouldn't it be 10, not 2?
1, 0.
Or am I wrong?
Yeah, that's right. Good. Yeah. So that's kind of your. I think that even my solution was solving that way. But if you're staring at yourself, I mean, this is a safer, okay? Safer way. But can I just use an 18 directly? And the answer is yes, you can. If you use that, you just know that you'll get a gram here. This is an additional layer of the thought, because if you multiply all of them, the only thing that survives here is moles, right? So whatever this is a mass per mole multiplied by number of moles, you'll get a mass. So this unit is carried out to this one. So you guys can still use an 18 gram, and then you know the answer should be an 18 unit of gram. That's another way to do. But this is to me the safer. I think that in the beginning, yeah, okay, whatever quantity that I'm dealing with, I'm going to, everything is converted into meters and seconds, such as the newtons and joules and even watts. And this is an MKS unit conversion, so whatever the symbol then means, itself defined as a kilogram, because I'm using all the MKS unit. That's one way to think about it. But we are getting so used to saying 18 grams per mole, and that's a little complication that you have to be careful. Anyway, if you put them everything, the mass of H2O in this room is about 6.2 kilograms. That's a lot of water, okay? So in this room, there's a lot of water, and that's why when you are doing the organic chemistry experiment, and water is such a problem for causing a side reaction, so that's why people put it in a container, purging with the nitrogen or argon gas, so that you have a dry condition reaction. The water is an acid or a base? Both, right? Mm-hmm. It depends on what you have, but it is very reactive and aggressive compound, and will really give you a complication.